Good morning. If I could ask you to grab that last cup of coffee, the last little bit of breakfast, and take a seat, we'll go ahead and get started. My name is Mark Christensen. I'm privileged to serve as the Dean of the Lyle School of Engineering, and happy to welcome you here this morning for our, I think this is turning out to be our first download of the season. Surprise, surprise, we had a projection of snow, and one of the things I hate about living in the South is when they project snow, if there is snow, I always get where I'm going before they decide to cancel anything. And so we canceled things the night before preemptively to make sure none of you had trouble trying to find a way to park. That download has been moved to May, and so now we're looking at a lineup where on April 1st we're going to have Eric Larson, fantastic professor from the computer science department, talking about deep fakes. So you've seen these things where they put President Obama's head on a different body giving a video in an election year. It's a great time to be talking about deep fakes, and so please come back, bring your friends for that one. And the rescheduled one will happen to May 6th, where Bruce Ganade from the Hart Center for Engineering Leadership, who runs our National Academy of Engineering Grand Challenge Scholars Program, is going to basically be doing a short introduction of the program and giving most of the time to the students who are in the program. So we'll have 4 or 5 students coming to talk about what they're tackling as part of that interesting program. If you haven't been with us before, the format is a talk that's 35-40 minutes long, plenty of time for questions at the end and to get you on about your day. On your table you'll see index cards with pens. If you have a question, you have an idea, there's something you want to bring up, go ahead and jot it down on that card. At the end of the talk, hold the card up. One of our staff will come by, grab it, get it up to me here in the front, because we'll do a curated question and answer with the speaker. That way we capture everything on audio, and I can throw anything I don't like in the trash so we never have to hear it again. So this morning's speaker is Professor Corey Clark. He has a joint appointment in the computer science department, and he is the deputy director of research down at the Guildhall. Many of you may know the Guildhall. The Guildhall is the #1 computer gaming program in the country. It's part of SMU and has been on the Plano campus since its inception, and the newest building on campus will be its new home. It gets the penthouse suite. Isn't that what you're calling it, Gary? The top floor of the new Ford building. As they come down, we're excited about how they're going to engage with us in research. And you're probably thinking to yourself, research and computer games, I'm not sure what that's all about. But if you've ever thought the youth in this country are spending too much time playing computer games, we're going to change your perception about that today. Because we're going to see that the time spent playing these games can actually be solved to solve real problems the world's facing. And one of the leading experts in that is our own Corey Clark. And so without further ado, let me bring Corey up and let's give him a warm welcome. Thank you. All right. Hello, thank you for all coming. Early morning with the rain and traffic. So today I want to talk about how video games are changing our society, have already changed our society, and how we can use that to make impact in the world. So my background, I started out in the Navy as a nuclear electrician, went into advanced research projects for the Department of Defense, and then started doing some consulting and other work, and then became my PhD in nanoscale growth kinetics, which has nothing to do with video games, but I started doing that with simulation work, which is what got me into video games, trying to harness that power, that's capability. We have about 14 people associated with our lab right now, all working on various projects. We're going to highlight a couple of them and talk about the video game industry in general to give you a better picture of what it's doing and how much it's impacting everything that you see and hear in the world. Our lab, the HuMIn Game Lab, really focuses on 3 different areas: video games, distributed computing, and machine learning or artificial intelligence. And really where we want to see is when those sections overcross, that's where we find these convergence areas that really allow us to do things that have never been done before. So we specifically do our work in any of those cross areas, but we've done it in some others as well. So the world is full of gamers. Right now in the world there is about 2.2 billion gamers in the world. That's about 30% of the world's population. You may look in the room and say, I don't play games, and I'm not a gamer, and the perception of what a gamer is probably pretty false. So most people think of a gamer, they think of somebody that's sitting in a basement playing some first-person shooter, just doing stuff, and that's it. But how many of you ever played Words with Friends, right? So if you've played that, you're now getting involved in games. In fact, that was a game developed here by some local group in this area. It's one of the most successful games ever launched.
Now, even if you don't play those games on your phone, you'll still find that you are being gamed. So something like LinkedIn, for instance. LinkedIn had a big problem. They were trying to get people to complete their profiles, and they weren't able to do it. Nobody wanted to spend the time to put the energy in and to give the information out. So what did they do? They put a badge on it, and they put a progress bar, and they gave you all-star status if you complete it. So they started giving these gamification techniques, and they increased their engagement by over 55%, getting people to fill in and actually start completing profiles. So even if you don't play games, you're probably playing them on some website or some service that you're using as it's trying to keep you engaged. It's because those loops that are created for engagement actually are very effective in how they work. So with that, let's start talking about some of the changes that we're seeing. So gaming is already changing entertainment drastically. Currently today, gaming itself as market is bigger than the movie and music industry combined. If you take all of that, there is more money produced in the gaming segment than both of those. So it's a very large scale market. It's like $140 billion a year, approximately. Gaming is changing TV as we know it. Most of the people that I know that are Gen Y or Gen Z, they don't even own TVs anymore. And they stream all their content online. You can look at something like YouTube, and it has about 2 billion monthly active users. And each of those users spends around 40 minutes a day online watching YouTube videos. And then we go to Twitch. Twitch is focused around video gaming. It is a streaming service just like Netflix or something like that where they're streaming content, but it's live. So it is this new substitution for TV. And the content they stream is around gaming. It is people watching other people play video games. And they have about 140 million active users each month. And of that, they spend 95 minutes every day watching people play video games. That's not even playing video games. That's just watching people play video games, right? It is a massive industry. You look at sports. It's definitely changing sports as we know it as well. This year, the League of Legends World Championship video game tournament had over 100 million viewers. It now surpassed the Super Bowl. So it is the most watched sports activity online ever, right? When you look at that, you can compare it to the NBA. If you take all the NBA finals and combine them, it is still smaller than one League of Legends tournament that happens online. So when we look at sports, and even this area, Dallas is the #2 market for esports. We have a couple of professional teams in the area, one of which we're partnering with, and it's making massive impact. So this is the largest growing segment when it comes to sports, and it's in its growth. And we're seeing it evolve every day. And every year it just keeps growing while other sports are trending down compared to Major League Baseball and NBA especially. So it's a very big area. So as you can see, it's already started to change our culture. So it's become much less of a subculture, and it is becoming the culture of our world as we see it, just by the numbers alone. When 1/3 of the world is doing something, that's not a subculture anymore, right? So it's also changing education as we know it. Bill Gates once famously said that game-based learning is the future of education. So why is that? How is gaming changing all of those things? It has to do with these concepts of flow and game loops, engagement loops. The whole point about gaming is to create a mechanism that gives you a challenge and it scales it to your ability to keep you highly engaged. We don't want the challenge to get too big to where you get frustrated, and we don't want it to get too simple where you get bored. So we dynamically adjust these to keep it right in your ability level. That is exactly what we want to do as education as well. If we overwhelm you and you can't grasp a concept, you end up leaving, overwhelmed, don't want to continue. Gaming provides a place where you can experiment. It's very experiential. And that whole concept of experiential learning is fundamentally how gaming works in the first place. You solve problems inside of gaming. In fact, if you didn't solve any problems in gaming, it wouldn't be fun. It is the challenge that actually makes it engaging for you. And we scale that accordingly. So by doing that, you actually create this high engagement loops, and we've taken games and concepts and adjusted them to make them put inside the flow, these flow channels, to actually keep that engagement happening. So when you look at that, what can you do when you have an environment where it is safe to fail, it is expected to fail, and you are expected to keep trying over and over and over again until you master and learn a concept? That is perfect for education. So we took that concept and we entered into a competition called the X Prize. And we went and launched a game to actually try to teach adults how to read. And Dallas DFW area alone, there's over 600,000 adults who are illiterate and lead below a third grade level. So our challenge is how to disrupt that market. So the Barbara Bush Foundation and the Dollar General Foundation put together an X Prize to actually go and try to disrupt that market. SMU was the only group that actually built something from the ground up solution. We competed against the worldwide competition, several other companies, and we actually ended up performing well. So we created a game called Codex, The Lost Words of Atlantis. We performed some focus study groups. We found out what these individuals, ranging from the ages of 18 to 65, how could we build something that engaged them all? Three of the biggest things that we took away is they wanted a sense of accomplishment, they wanted world knowledge, and they were self-conscious about their reading ability. So we took those concepts and we transformed them. For the accomplishment, one of the big things they said they wanted to read a book. So we used libraries and bookshelves as our progress meters. And as you progress, you were putting books on the shelves. And they felt that sense of accomplishment as they were moving through the world learning new content. They felt very isolated based upon everything they had seen. They aren't able to communicate and read, so they wanted the ability to learn more about the world. So they were a traveler. They're an archaeologist uncovering these ancient language and tablets, trying to decipher them. And in that, they visit the world's most fantastic places like the Sphinx in Egypt. And as they master a level, the game interface is removed, they see the real place, and they learn about what that place is. So they visit the Antiquities Museum in Egypt, or the Sphinx, or the pyramids, for instance. We have several locations they can go. The last piece was the self-consciousness, and this was the tricky one. We needed to create a way that not knowing how to read was not a hindrance, and that everybody that playing the game would have the same experience. So what we did is we created an ancient language with an interesting font that nobody in the world knows how to read. It's some unknown language, and your job is to figure it out and decipher it. So you learn it letter by letter, sound by sound. And anybody that plays that game, there is no expectation for you to understand how it works. So therefore, the self-consciousness of not understanding how to read was removed because everybody starts at the same level. So by combining those three things together, we created an interesting style of gameplay where there are hidden objects inside the world. You're going around trying to craft these words together and actually to decipher this ancient language you can see in the different tablets. And as you complete it, if you max out and master each level, it will then provide you a reward, and that reward mechanism will then show you this, in this case, the Sphinx area itself. So this was fantastic. We did some pilot testing on our own, and in that pilot testing, we did 8-week study, and 60% of the people that actually were participating in the pilot test had more than a 10-point increase. That was a year's worth of learning in 8 weeks. Everybody that participated in the pilot actually increased their literacy level. We published some papers, and it was presented at the American Educational Research Association, as well as a ACM paper that we published here out of this department. We created a backend that collects large-scale data. We collected every click of every person on the screen so that we could understand how they interacted, how they learned. And our next set of phases of this is actually to try to use machine learning to dynamically adjust the game in real time based upon how they're participating. So if we can use machine learning to optimize that experience, we can get people to where they need to go faster, keep them engaged, and help them tackle this problem. Our system is highly scalable. It was able to handle up to over 10,000 concurrent messages coming in per second. And we're still running today. We have over about, I think, around 3,000 people currently actively on the platform. And it worked well. It worked so well, we won the grand prize. And then we also won an achievement prize. Thank you. So it was an awesome opportunity. We actually tied for the grand prize. We had the largest gains for non-native English speaking, for specifically we targeted Spanish speaking. And then the other company that won the grand prize had focused more on English speaking, and they achieved the highest in that. But we both achieved the same level of gain, so that's when we tied for the grand prize. So it changed education, and it's changing it currently. It's also changing how discovery happens. One great example of this is Folded. It's probably one of the biggest first. And this was a 10-year protein folding problem that they had tried to use machine learning, supercomputing capability, all of this to try to solve, how do I fold these proteins? And they were kind of running to the end of their money, their opportunity, the grants. So they partnered with the gaming school at University of Washington, and they built a game called Folded. And in 10 days, they actually found the solution that had eluded them for 10 years. with 53,000 gamers. And so the idea is that computers are great, machine learning is great, but when you get humans involved and you start partnering them together, big things can happen. And we're going to talk more about that theme as we move forward, but this is one of those first examples as we step through it. So we know video games are big, we know they're making a change. So let's look at how we're partnering right now to make this happen. We have a large set of data from the drug discovery group here at SMU. And we've taken that data and we're trying to now build gaming interfaces around it to see if we can perform those same sort of actions with gaming and computers at the same time. We took the data, it's around chemotherapeutics and it's co-medications to try to make multi-drug resistant cancers now treatable. And so we built this simple interaction here, and the goal was, as a gamer, you're going to move these levers around, and your whole purpose is to turn that whole block on the bottom right-hand side green. So you start out with something that looks like this, and what we saw after about 20 minutes of this horrible gaming interface, we got people to get it to here. So we knew we had something in place. So we actually partnered with Balanced Media Technology, which helped take and build out game content for us so we could put the research inside of it. And they launched a game in Minecraft in itself. So this was a modified version of Minecraft. And you can see right here, this little area inside mimics this exact thing that we had prototyped out. And with that, we put on an on-scale or an online event at scale with these 4 streamers that were on Twitch and Mixer. In that 1 2-hour event, we had 1,700 people online. We were able to analyze over 500 retinal images, as well as process over 1,500 cluster compounds through that gaming just by playing Minecraft and having people watch. So it was that crowd that was there that was highly engaged, doing something for the fun of what it was, actually was able to be reutilized and repurposed to do something big for us. Balance also took these concepts and started putting them in other games so that we could utilize them. So here's that exact same game, but it's now being played as a shooter game. And you'll notice that whenever you pop into this area, this is that same interaction with that sheet. So now right there, that is actually processing cancer data. You're actually moving things around, trying to help us sort it out. So this one mechanism right here is a emulation of how you would do distributed clustering algorithms, but it's now human-centered. And we can couple this with algorithms to actually make the machine and the human doing the same thing at the same time, so that whichever one finds the best answer, it feeds it to the other group. So now people are playing a game, solving a problem, while the computer is trying to run the same algorithm. And some for the more old school, there's Qbert, right? And this is around feature selection. So this is reminiscent of a similar as a binary particle swarm optimization or random forest selection. And as you're jumping from tile to tile, you're actually selecting which features should we be looking at inside of the data set. So you're turning them on and off to see if you can improve the score. The last thing is that those 2 games were both then modified again to make them compatible. The one on the left is called Omega Cluster, and we'll actually launch something with that recently. And the one on the right is a game that you can download right now from any of the app stores, computer, PC, whatever you want, called Rocks and Runes. And while you're playing that, you're actually helping us select which features we should be looking at inside of the cancer compounds. So this is a similar game to Candy Crush style, but now the gamers are being empowered, doing something they want to do no matter what, but it's actually giving us capability to do some research here. That Omega Cluster game was then worked, and I think it was about 2 weeks ago, was a partnership between Complexity Gaming, which is the Jerry Jones esports team up in Frisco, Balanced Media Technology, and then SMU and our game lab. And there was a worldwide World of Warcraft event. You may not know World of Warcraft, but it's one of the biggest games in the world. Blizzard, it's what put them really on the map for their scale and business. We took that, and there was over 11 million people over a 10-day event that tuned in. Of that, we had over 55,000 minutes played of Omega Cluster, just sitting there on the screen while people were playing or just watching others. So this is, think of it, interactive TV. People are watching something during a commercial break or a downtime. They just start playing this little game just to kill some time. But that has value, and we're actually using those moments of time to actually do something bigger for us. In that time, those 55,000 minutes basically equates to 23 40-hour work weeks is how much work we got out of that crowd in 10 days, right? So it's immense when you start looking at the capability and what you can do. This is one event. These events are happening all the time all over the world. And so this is a scale of a problem where you have now massive crowds of people that are interested in doing something. And if you can tap into the gaming aspect of it, you can empower it to do so much more. That comes into AI. So we know that AI itself is changing the world. But I think it might be better to try to explain AI in a concept so that we can all be talking on the same language and page. So I think the best way to explain AI is by using piñatas. So this is essentially what an AI algorithm is like, right? It's a blindfolded algorithm, and this is, I would say this is a candy finding algorithm. Its whole goal is to find candy. And it's swinging that bat as randomly as it can, hoping that it makes contact. And as soon as it makes contact, it'll keep hitting in that same spot until it tries to get better and better. But this, as you can see, doesn't always work well, right? And we think of AI today, it's about the intelligence of a 2-year-old or 3-year-old. It's not very much beyond that. So this works great if it knows where the actual piñata is. If it doesn't know where the piñata is, it can waste a lot of energy and a lot of time. So what if we start coupling the AI with humans and they start working together like we're seeing in these video games here? Whenever you guide the AI, because you know the area it needs to be looking at, you get a much more effective candy searching algorithm. In this case, you can see whenever you have somebody guiding it that actually knows what's happening, you can actually be much more effective. Now, there are actually learning theories that back this up. When you look at experiential learning, that is a whole learning theory that exists. And that's how AI is kind of based right now. What we're doing in our lab is saying that we need to look at the other learning theories that have been used for humans for decades. And one of them is called Constructivism, or Constructivist methodology. And that is, don't just do the experiential part. If you have a mentor or a guide that can help point you in the right direction, you can save massive amount of time in trying to learn something. You can still do that experiential part, but they can guide you away from pitfalls. And that's exactly what we're talking about here today. So if we add those humans with the AI, we can get much more powerful and capable algorithms. Now what happens if we connect it to gamers in the crowd? It gets a lot bigger, right? At that, you're talking about scale. So now we don't just have a few people whacking the piñata, we got everybody whacking the piñata. And all of that combined together now creates these highly capable, engaged algorithms that can solve really large-scale, difficult problems. So let's talk about one of the problems that we're currently working on, which is OCT image analysis, and it's a partnership that we have with SMU, Retina Foundation, Johns Hopkins, and Bounce Media Technology is also assisting with the platform on it. The whole goal of this problem right now is to actually be able to identify macular degeneration inside of the eye. So on the left are two different images, the same image, before and after being processed. And the whole goal is to find these humps. These humps are actually the drusen inside the eye, and being able to identify them accurately and precisely is very important. If we can measure the growth in a more precise manner, then we're able to actually determine if a medication is working or not working. And the more precise you can make that, the less change that has to actually happen to verify that the medicine is actually working. The current problem is that these algorithms are not really effective at actually finding these humps properly. And so what ends up happening is that experts in the lab have to go back and manually adjust what the computer finds. So I don't know how well it shows across here, but you can see there's two lines. On the top one, a red and a green. And at the bottom one, the green line's moved down because it's trying to find the min and max for this area, for these two different layers. So Bounce created a game called Eye in the Sky, and it allows us to perform the research that we're doing. So it is essentially a tower defense style game, and people are trying to figure out where these tanks and these mech warriors are going to be moving around inside of the environment, and they're trying to predict that path. And the better they predict it, the more tanks and things they destroy. But really what they're doing is they're actually helping us train them on to be able to analyze and segment these images for us. So here is a little video of the game. So you can see here, this is the OCT images. You can take this exact image. It then goes through a gaming kind of transformation. Now it looks like satellite imagery. And in that, the players are, you can see here, moving around, trying to trace the path of where they think the mech warriors are going to come. And as they finish the two layers we're currently looking at, they say yes. And now the satellite orbital system is trying to blow up things that travel across that path. And how good you predict is how good you actually matched the segmentation algorithm and the training process of the game. And so what we actually saw is, well, how well does it work? So the first image on your left is actually the results obtained from the very first level of anybody ever seeing the game. Now understand, we didn't tell them you're segmenting OCT retinal images. We didn't tell them anything that you're doing. We just said, play the game, right? Just play it and try to blow up the tanks and the mechs. That's all we had to do. And you can see at the very beginning, first level, the answers are all over the map. They don't really know what they're trying to do. They're trying to figure it out, trying to figure out how the mechanics work, the gaming loop works. And after about the fourth time, you start to see a major convergence here. And now all the results are getting much closer to really where the disease is inside the eye. So this actually was recently published at the end of last year, and it showed that we were able to train a gaming crowd just by giving a game to segment images at the same resolution and capability as somebody in a lab. We were within about 1 pixel difference than where the lab is. And even between two different people segmenting the same image in the same lab, you get around 10 pixels difference. So we're well within the margin of error there, and being able to have a crowd of gamers actually do something that currently is expensive and time consuming inside of a lab. So that's where most of these citizen science style games, this human computations game, this is where they stop. They're trying to make the gamers actually find the answer. But I want to go back to where everybody's banging on that piñata together. I want to make AI and gamers work together. So what we did is we didn't want to find the answer, but we wanted it to augment and work with machine learning algorithms. So we took that game and we actually created a filter that's then applied to that data set. And what that filter is, it's actually a suggestion. It is a first guess of where a human believes the disease is inside the eye. And what that does is that we still have their whole image, so the AI is still able to see the entire thing. It just now knows that at least somebody thinks right in this one area is the disease. So how does that, by applying that simple input, how does that affect the overall effectiveness of an algorithm? So one thing we can see here is this is actually a deep learning algorithm in action. The pink area is the algorithm trying to figure out where these two lines are. And so the pink area is where it's currently looking. So the bigger the area, it's looking more all over the place, and you start to see it kind of focus in. You'll notice on the left that the area focuses right around the lines and very quickly converges to understanding where those lines are inside of the image. That is because it has a human filter being applied to it. The one on the right just has the image. It has no guesses, and it's just trying to figure out where the lines are. And you can see it spends a lot of time wasted looking in the wrong spots. We know the right answer. Can't we just help the algorithm along? And that's what we do. And we can see right here that it dramatically reduces the time it takes for the algorithm to actually learn how to find these things. So we took that and we applied it and we said, okay, now let's train something with it. And so we tried to train an algorithm to do this segmentation, and we started out with the algorithm running on it just in the standard, and that's the gray. So the gray is what the standard deep learning algorithm does on its own. The orange is what happens when you actually add the human filter inside of it. So you can see this is a relatively short epic. It's about 23 cycles. Normally you would have something going into the thousands of the number of tries it would need. But after 23 cycles, our algorithm is already close to 99% accuracy, right? And being able to identify the disease state in the eye. Whereas the standard algorithm is still about random guessing. 50% is about random guessing. Is it there or not? There's only two options. So it never really progressed outside of that area. So we were working on a grant, and we needed to try to get some data. So we actually then passed in some images that had extra complexity in the pathology on them. So this is geographic atrophy inside of the images. So they had never seen anything like this. They had never seen any images like this. And our goal was to actually see what would happen if we gave an algorithm something it had never seen before. Could it actually still find the disease in the eye with this really complex capability around it? We honestly expected it to fail, because that's what every machine learning algorithm would do. If you actually gave it something it had never seen, some completely different test case, it usually does not perform well. So we can see here the blue is correct, and the one on the left is actually our algorithm, and the one on the right is the standard methodology as well. So we took 97 images and we started to process them. And so with this pathology. So this is accuracy. And accuracy is not really the right measurement here, but we'll explain that in a second. So you can see on the left-hand side, we're looking at two different boundaries, and the first one's on the left. The green is the standard algorithm. The blue is our algorithm. So you got to remember, 50% accuracy, a monkey can attain 50% accuracy because it's just hitting a button, yes or no. It doesn't have any conscience of that. And that's exactly where it sits. It sits at 50% accurate. So that's not really very effective, right? So on the other side, it gets a little bit better, more in its accuracy for the second boundary. So what we really wanted to look at was more precision, because this looks at the percentage of times that it actually correctly guessed. So we're looking at false positives compared to false true positives. And that's much more of an indicator of how well the algorithm is working in this case. So it may be hard to see, but the green algorithm is still up there. It's just so low on the left-hand side. Its precision level is between 0 to 3%. It was horrible. But when we added that human filter in it, we were already getting, around 90% capable in one of the boundaries. The other boundary, the algorithm was a little bit more capable. It's maybe around 30%, still nowhere near usable. But the methodology we're doing by using that gaming interface to create this filter that's then added to the image put us in the 90% point. So without even pushing this very far, we're already getting close to usability as far as capability goes. So we definitely know we have something here. This is actually currently going up for publication right now. We're in the process of writing this out. So it's a pretty good find for us, So we're calling this new methodology of actually taking humans and machines and working together, Constructivist Augmented machine learning. So it's really about machines and humans working together, and humans being this collaborator, this mentor to help guide the algorithms in an effective way. There are multiple ways for us to do the integration. One is you can take subject matter experts and just have them provide the input. You can do it through crowdsourcing and human computation gaming, which is what we did with the retina problem. You can actually use it for bias detection and data enhancement. You can actually have it modify loss functions inside the algorithm. And another thing that we're currently doing that's pretty cutting edge is actually changing how actually machine learning works altogether. And actually, instead of just the algorithm working on its own, humans actually open it up, look inside, and make those corrections. We're actually seeing opportunities where we can identify where the algorithm's going, make manual adjustments inside of it, and we were able to see it jump in performance what would take in about a week of supercomputer time to get there, just by human making an intuitive leap for it. And that's the thing, to make those intuitive leaps is very difficult. That's not something machines do very well. So we can put those unstructured data sets, we can see patterns in different ways that computers do. There are things that computers do much better than us, and we should let them do those things. But there are things that we do much better. And together, we can do much more than we could either one of us apart. So whenever we put all these things together, you get four kind of really big takeaways. You get faster training. So now I'm able to create machine learning models much faster than ever before. I can actually make them smaller. Because the algorithms are actually partnered with a human input, they don't have to learn as much. So I don't need these massive scale models. I can actually make models that can now run on cell phones and embedded devices, IoT on the edge, because they don't require as much learning to get to that final answer. Higher accuracies. You saw this directly with the retina. Because the algorithms are able to be trained faster on smaller data sets, that you can actually get to those accuracies quicker, and it becomes very beneficial. And the last piece is reduced data sets. So big data is a problem. Data is doubling every 2 years. And one of the big things about data is you may have it, but it's not usable, right? And so how do you get usable data to actually get these insights out of? And that can be very costly. There are markets right now where just labeling and segmenting data is a full business. Appen is a company that has two main customers, Google and Microsoft, and both of their customers spend about $20 million a month to label and segment data. It's so expensive, it's time consuming. A machine can't do it on its own. So you literally have to have somebody do it, and they got to do a good job. And so what we're showing here is that you can actually reduce those data requirements by actually partnering with a human. It doesn't take as much because now the machine is taking some of the insight that's gained by the human itself. All right. That's it.
So as I said, if you have questions, jot them down, raise them up. Somebody will bring them up to me. We've got something to start off with here. So X Prize, tremendous success. What's next for that team?
So yeah, so our next big part of the X Prize is actually, we're talking to a couple of groups right now that are asking us, what do we want to do? And what I want to do specifically is to actually take this technology and create these machine learning models that can help guide students. And so make an adaptive educational system. One of the things that we learned is that some of the actual students themselves just had holes in their knowledge. Like they didn't understand a couple of letter sounds. And if you fix those holes, their ability to learn skyrocketed. And that's why we had so many people that just jumped so quickly in 8 weeks. So we want to be able to automate that problem to actually have AI that can find those holes and then plug them. And we're actually looking at not just doing adults, but family literacy and using AR to help parents and kids get engaged by reading text content as well.
So put on your prognosticator cap. Okay. How do you think gaming is going to impact public schools and politics in the next 2 decades?
So I think it's going to have positive impacts. I think you're going to find it in public schools because it's so effective in the model. I mean, we recently won a NSF grant to actually take Minecraft and put it in schools to help teach computational thinking and computer science. And specifically, we're looking at machine learning in junior highs and high schools. The other big thing that's happening is that as the population ages, the people that are coming up into these new positions in politics are from a gaming culture. They have been gamers for their entire lives. It is not this idea that is so far out to them. So as we get that rotation happening, you're going to find gaming is much more accepted and much more used. And we're already seeing that happen. My generation was probably the first generation to fully grow up with gaming its entire life. And we don't have the same stigma as my parents do with that.
What corporate companies are knocking down your door?
Corporate companies. We're talking to a few right now. So when it comes to the business side, there are some insurance style companies and foundations. For the research side, one of the groups we worked with was Raytheon. That same Minecraft game was actually utilized to solve a cybersecurity problem trying to identify money laundering, which is a similar clustering problem. And that's one of the big things that this capability and the way that we're proposing it is that it's not problem-centric, it's algorithm and data-centric, so the games are reusable. So we can reuse the same games for new problems and actually keep this moving forward.
Why use video games at all? Why not just have subject matter experts partner with machine learning techniques?
So that's a great question. And the key is that you don't necessarily have to use gaming. But what happens is that if I can take a gaming group and actually give you the same results that a subject matter expert would have in the lab, that subject matter expert can now go do something else, right? It's about that partnership. It's not about replacing people as much as it is about being able to get humans to do the things that they can do well.
So I think this is actually a fine point of one of your slides that might have been lost. How did they find or recruit 50,000 users?
So specifically for Folded, they launched it in a game community. They go out on these websites, they partner with different influencers. And that's essentially what we do as well. So with Complexity, where we had 11 million people tune in, that is a professional esports team. That would be like the Dallas Cowboys doing a game saying, hey, we're going to play a game. Who wants to come watch it? You get a lot of people in that. So you work with the influencers that actually have these massive crowds of people that watch them, pay attention to them, and will actually participate in any of the things that they do.
So you had a graph that showed your algorithm approaching 1 and the standard algorithm diverging away from it around Epic 4. So people wanted to know why the standard algorithm all of a sudden started doing worse.
Because it's swinging a bat at a piñata and has no idea what it's doing, right? I mean, it's literally just trying. 50% isn't good. That's random guessing. So it's not necessarily diverging as much as it's just trying to look. It hasn't really found a good answer yet. And so it keeps looking in all those different areas. And if you go back to this guy, you can see, I'll make this one play, here that initially the algorithm is looking up at the top at the right spot, right? But then it hasn't really found the answer, and it's still looking at the whole thing, and it actually gets worse as time goes on because it's starting to converge at the bottom, which is actually the completely wrong direction for it to go. That's why humans can really help it out, right? And that's why you see that divergence in there. It's more of a, not really a divergence as much as it never really found a good answer in the first place.
So a research suggestion in the form of a question. Is SMU involved in predicting the spread of the coronavirus?
I know that there was a hackathon a month ago, a couple weeks ago, a large-scale one, and one of the winner groups was actually an app to look at the spread of the coronavirus. But I am not actively doing that, and I definitely can't speak for SMU as a whole. So.
All right, so deeper question. How does the integration of humans and machines affect bias and ethical concerns in AI?
So I think this is actually one of the biggest areas that we can actually take advantage of with this. So right now, we know that data has bias. If you look at any sort of system where Amazon had this problem where they were trying to automate hiring, and then they found that their algorithm was only picking males because how they found their data was actually from all the resumes that they had. And so the wording of a resume then changed how it would predict if somebody was going to be good or bad. So, and the problem is they completely removed that whole system because even if they fixed that problem, they couldn't be sure if there was another bias hidden somewhere else that it started, being biased towards, right? So by actually adding in this human component, we can actually tell the machine whether or not its decisions are good. We can actually help adjust this dynamically. These inputs that we're passing in along with it are dynamic inputs that are coming from humans. So it's not just making a decision on its own, it's making its decision with a recommendation by a person. And so when you look at bias and even understanding of that, those biases change over time. Sometimes bias is good, sometimes it's bad, right? And so we may want to adjust bias over time. And it's actually a problem with the retinal data is that the science has been evolving every year. And where they think the disease is in the eye is changing every year. So there's not even a single good data set that is pristine, that has the right answer across it. So by actually adding in this human capability, we can now adjust bias and dynamically by having this human portion added to it.
Awesome. Let's go ahead and thank our speaker.